Let's talk about energy. It's kind of the currency of our entire universe, right? It lights up our cities, it powers every piece of tech we own, it fuels our very bodies. For a long time now, we've gotten it by burning stuff, splitting atoms, or grabbing it from the sun. But every single one of those methods has a pretty serious world-changing downside. And that brings up a really, really big question.
I mean, the sun seems to have it figured out, right? A seemingly endless supply of clean power. So, what if, and this is a big what if, we could build our very own tiny sun right here on Earth? Well, that is the massive, audacious dream of nuclear fusion. In this explainer, we're going to dig into how it's supposed to work, the absolutely monumental challenges we're up against, and the multi-billion-dollar bet that humanity is making to finally bottle a star.
I mean, just look at the contrast. On one side, you've got our current reality. Fossil fuels are literally cooking the planet. Nuclear fission, it leaves behind this toxic garbage that stays dangerous for thousands of years. And renewables, which are fantastic, well, the sun doesn't always shine and the wind doesn't always blow. But then there's the fusion dream. A future with clean, safe, and nearly limitless energy. Enough power to create whole new industries, turn deserts green, and give every single nation on Earth total energy independence. The stakes? They couldn't be higher.
Okay, so if we're going to build a sun, where do we even start? Well, first, we need the recipe. We need to understand how a star actually works.
The first ingredient you need is something called plasma. To get fusion going, your fuel has to be so ridiculously hot. We're talking millions of degrees that the atoms literally fall apart. The electrons get ripped away, and you're left with this superheated soup of charged particles. Now, here's the crucial part. Because those particles are charged, we can grab onto them and control them with magnetic fields. And that right there, that's the whole secret sauce.
But, of course, there's a huge problem, a really fundamental one. All those atomic nuclei floating around in that plasma soup, they're all positively charged. And what do like charges do? They repel. Think about it like this. Have you ever tried to push the north poles of two strong magnets together? They just refuse, right? They push back. That's exactly what's happening here on an atomic scale.
So how do you get past that? Well, the answer is just brute force. You make them go incredibly fast. See, in this game, hot just means fast. We heat the fuel up, turn it into a plasma, and get those nuclei moving so insanely fast that their sheer momentum lets them smash right through that force field of repulsion. They collide, they merge, they fuse. And when that happens, a brand new element is formed, and a tremendous amount of energy is released. That's the jackpot. That's the energy we want.
So what's the actual fuel we'd use? It's basically a cocktail of two special types of hydrogen. First up is deuterium. It's totally stable, and the best part? It's super common. You can find it right in regular old seawater. The second ingredient is tritium. It's the perfect partner for deuterium to get a really efficient reaction, but, and this is a huge but, it comes with a major catch. It's radioactive, and as you're about to find out, it's one of the rarest things on the entire planet.
Okay, so the recipe sounds simple enough on paper, right? Heat, squeeze, fuse. But trying to actually cook this up on Earth, well, that's where we run into some absolutely massive challenges. The science is one thing, but the engineering, that's a whole other monster.
Right now, scientists are basically chasing two main strategies. The front runner is called magnetic confinement. This uses a giant donut-shaped machine called a tokamak to create these incredibly powerful magnetic fields that basically form an invisible bottle to hold and squeeze the plasma. The other method is just pure brute force. It's called inertial confinement, and it uses the world's most powerful lasers to blast a tiny little fuel pellet from all sides, causing it to implode on itself and for a split second, fuse.
That magnetic bottle idea sounds pretty slick, right? Just trap it in a force field. But the plasma itself, oh, it has other plans. This quote just says it all. The plasma is this wild, turbulent, chaotic beast that is constantly writhing and trying to escape. Controlling it is one of the most complex physics problems humanity has ever tackled.
And this right here is the absolute biggest roadblock, the holy grail of fusion research for the last 50 years. Net energy gain. We've made fusion happen tons of times. That's not the problem. The problem is it's always been a money pit, energy-wise. We have always had to pump in way more energy to heat everything up and run the magnets than we've ever gotten out from the little puff of fusion we create.
Okay, remember tritium, our perfect fuel? Well, take a look at this number. 20 kilograms. That's it. That's our best guess for the entire world's supply, for the whole planet.
And most of that is already spoken for, locked up inside nuclear warheads.
Now, what's this number? 300 grams. That's how much tritium one single commercial fusion power plant would gobble up every single day. Yep, you did the math right. We'd burn through our planet's entire stockpile in about 2 months for just one plant. Talk about a supply chain problem, huh?
So, faced with this, slightly terrifying fuel crisis, scientists are cooking up some solutions that sound like they're straight out of a sci-fi movie. The main idea is to actually breed new tritium inside the reactor itself by lining the walls with lithium. But an even crazier idea? Go to the moon and mine a different fuel called helium-3, which the sun has been blasting onto the lunar surface for billions of years. Seriously.
So, you've got this unstable plasma, a massive energy deficit, and basically no fuel. With all these insane hurdles, you gotta be asking, why are we even still trying? Well, it's because the jackpot is so unbelievably huge that the world is willing to place a multi-billion-dollar bet.
There's this old joke that's been around forever in physics. For decades, whenever you asked a physicist when we'd have fusion power, the answer was always, oh, about 30 years. It's easy to be cynical, but right now, humanity is making its biggest bet ever that this time it's really different.
And that bet has a name, ITER. It's located down in the south of France, and it is a colossal international project. You've got 35 nations all chipping in to build the biggest, most powerful tokamak reactor in the history of the world.
And here's the price tag, just to get it off the ground. $10 billion. And let's be real, that's probably a lowball estimate. This makes it one of the most ambitious and expensive science experiments humans have ever attempted. It is a $10 billion wager on our energy future.
But what's the goal of this $10 billion machine? It's simple, and it's everything. Achieve a massive net energy gain. The whole plan is to pump in 50 megawatts of power to get things started and get 500 megawatts out, a 10-to-1 return on investment. If they pull this off, it'll be a first in human history, proving once and for all that this crazy idea can actually work.
So, where does all this leave us? Is this the key to our future, or just the most expensive science experiment flop in history?
All right, let's break it down, the final tally. On the pro side, the dream is incredible. A practically limitless fuel source from seawater, zero carbon emissions, no long-lived radioactive waste, and a design that's inherently safe. It literally can't melt down. But the con side? Man, it is a sobering dose of reality. The tech is totally unproven at the scale, the cost is astronomical, and we literally have to invent new materials that can survive being next to a miniature sun for years without falling apart. And here's maybe the biggest, most overlooked question of all. Let's say it works. Let's say ITER is a huge success. Can we actually afford to build these things? Right now, we are watching proven, clean energy nuclear fission plants shut down because they just can't compete on price. Fusion reactors are going to be even more complex, even more expensive. Are they doomed to face the exact same problem? Look, it's a ridiculous gamble. The challenges are just mind-boggling. But it all boils down to one final, huge question. When the prize on the table is unlimited, safe, clean energy for every single person on this planet, forever, is building a star on Earth really a risk we can afford not to take?